Up there is my daughter's monkey named Monkey, who will be doing a death-defying stunt today later on. See how that goes. I wanted to go over the plan for the next 2 weeks because it's a little complicated. So today we're just finishing up. We're working on section 4.4, sort of these 2D force problems. 4.5 is the projectile motion. That's why the monkey's up there. And this week in practicals, I've given a warm-up test. It's actually based very, very closely on last fall's midterm, or last fall's term test 1, except we didn't cover quite as much content, so this one covers all through chapter 4, like your term test will. In fact, it's very, very similar, exact same format as what you're going to be getting in the actual term test. So, and then Wednesday, we'll come back here, we'll finish off chapter 4, and that'll be it for the testable content for the Tuesday's midterm. We still have class on Friday. I will talk a little bit more about exactly what to expect for the term test, where to go, and everything like that. That's the last class we have before the term test, because on Monday, October 10th, the entire university is closed. If you come here, you'll find that all the doors are locked and there's nobody here because it's Canadian Thanksgiving. And we Canadians take this Thanksgiving pretty seriously. It's all closed, right? The banks are closed and all that. So, after Friday, the next time we will meet will be in the evening of Tuesday. Okay. So, also on Friday, I'm going to start in on chapter 5 stuff. Hopefully, you guys want to listen to me talk about that on a Friday afternoon. But it won't be on the Tuesday's test. It'll be on the, I guess, November 15th test, if that makes sense. I'm just going to start going ahead with chapter 5 since we have that time. And then also next week, there are no practicals. Otherwise, it gets really messed up with the schedule to have a missing Monday and all these things, and so we thought we'd sort of just give you a break from practicals next week, and they resume on October 17th to 21st. And we'll be doing experiments on Chapter 5 and Chapter 6 stuff. I think that's the plan. And I just continue on to Chapter 5 and just forging ahead next week. That's the next couple weeks. You guys good with that? Any questions about that stuff? Otherwise, we got some thumbs up, so that's good. Beg pardon? I like how you're holding your mug. Oh, all right. It's just water. It's already fully caffeinated already. I have to watch how much coffee, or I get really. I have in the past. I've had a little sign here that says "Slow down, Jason," because I tend to talk too fast to get really excited when I talk about physics. So you can always yell that out sometimes. Slow down, Jason. See if that works. Oh yeah, and then April always wants me to remind you of this one, is that if you have some sort of time conflict about on Tuesday evenings, that you have to sort that out somehow. There is a sign up for alternative sitting button on Quirkus, and the deadline for that is today to register, because we have to book a room for you and get you settled into a place and time which you do not have a time conflict. Because you gotta write the test for those points. Okay. Yeah, so let's talk a little bit about this friction, because this is what sort of where we left off last time. N being sort of the normal force. In this case, I think what they're showing on this diagram here, which is a kind of an interesting diagram, is you've got something called an applied force, meaning that there's a hand or something applying a force. I'm always a little confused at what applied force means, but I think what it means is just somebody's pushing with a normal force. And it might be a human. This is called applied force. I would call that the normal, I guess, from some human hand or something, the hand. So that's supposed to be a diagram of a hand. And so there's the applied force, and then in this, the way I've written it here, lowercase n is the normal force. So I think that your textbook often uses uppercase, and then mg is the downward force. And then there's another force on this backwards, which is the static friction. And so as the applied force increases, the frictional force just matches it. This is sort of a 45-degree angle line from here to here, in which the static friction force equals the applied force. If there's no applied force, there's zero static friction, because it's an as-needed self-adjusting force. Okay. But it gets up to some maximum right here, the maximum, I guess, static frictional force. Okay. I guess it's the maximum frictional force too, because when it comes down to kinetic friction, it seems to usually be less, and that is because we have this experimental result that mu sub k, the coefficient of kinetic friction, tends to be less than mu sub s, the coefficient of static friction. Okay, and then in this case, constant speed. So I guess what happens is the person decreases their applied force to give it, so it's pushing along the constant speed. And so in this case, actually, the friction also balances out the applied force, but it's because you've lowered the applied force and sort of reacted. And so over here, what's happening is F sub k is always equal to mu sub k times n. It's one of the two forces that's not self-adjusting. Gravity is not self-adjusting, and kinetic friction. Those both just have nice little handy equations that you can look in your aid sheet and get them. It's the bad ones are static friction, tension, and normal force. Those are the ones that are as needed, so you have to solve out your force diagram. Okay, so let's do a quick example, and then we will do a demo and a little learning catalytics question. So if this is, it says at what angle is it just about to slip? So often in word problems, you have to kind of parse what it's saying. What this is saying is that Fs equals Fs max. So we've got B is the block. I'm going to call S the surface. This has a mass, I'll call it M. We'll assume that the block is at rest. Block is at rest. Let's just put a line down here, and we will say that this, we'll call it mu sub s, is coefficient of static friction. We'll just define things here. That's what's going to be important. We can draw a little theta here. That's the angle that we're trying to find. Find theta, which is a circle with a line through it. We're going to say that the sum of all the forces in the vector sense is equal to 0. So let me just draw the force diagram. We've got the normal force of the surface on B. We've got the static friction force of the surface on B. And we've got the gravity force of the Earth on B. So I think those are the only forces on it. And I think the trick that I will use, we'll do a trick, is we will tilt the axes. Tilt. You don't have to do this, but this one will save a bit of work, I think. I'm going to set y to be in the direction of the normal force and x to be opposite the direction of the static friction force. So when we do this, n sub x equals 0 and f sub s in the y direction equals 0. And that'll kind of help us with our equations. We only have one diagonal force in this case, and it's gravity. So you just have to be careful with that diagonal triangle for gravity, and that's it. So I can do that right now. If this is mg down, then I have to think about how I'm going to use components to make that. It's going to be a plus x component and a negative y component. So if this is like fg in the x direction, and this is like negative fg in the y direction, and there's a theta somewhere in there, which is either up here or over down here, and I think that it's down here by some kind of geometry rule. But what I do sometimes with these is the angle seems to be less than 45 degrees, so I make it nice and less than 45 degrees, and then the smaller angle here, theta, is I think the smaller angle here. So, but you must be able to figure out some geometry way of getting it down there. But you need that. This is the just about to slip condition. To slip, what does that mean? Implies that Fs equals Fs max, and that has an equation, mu sub s times the n. Okay. So, F G in the x direction from this triangle here is going to be the sine, so mg sine of theta. And Fg in the y direction is going to be negative mg cos theta. Hopefully you can sort of see all the trigonometry of how I got those, because those are super important. There's usually one or two forces that are on the diagonal when you set up your axes, and then you have to do all these right angle triangle things in trig. So now I'm ready to do the sum of the forces, which are going to be 0. So F sub x, the sum of all the x forces equals 0. What's that going to be? Well, it's going to be positive from the gravity, mg sine theta, and minus from the static friction. Let's try to divide this into x and y. So if I can sort of plug in this and solve it out, I get that mu sub s times n is equal to mg sine theta. Okay, so I guess that's as far as I'm getting there. The sum of all the forces in the y direction also equals 0. That's going to be the normal forces up, and then the gravity is down, mg cos theta. So I can solve that out. N, which was an unknown because it's self-adjusting, is mg cos theta. Okay. Now what am I trying to do? I'm trying to find theta, remember? Let's not forget that. So I've got two equations and two unknowns here. The unknowns are the normal force and the theta. So whenever I have two equations, two unknowns, I can solve for both of them. And the one that I care more about to get the answer here is theta. So usually what I do is I want to eliminate normal force. So I solve one equation for normal force and plug it into the other equation. And you'll see the n disappears. That's my trick. Let's do solve for n and plug into the other equation. When you plug it in, it disappears. So which one's which here? So actually, it's already solved. Let's just do there, right, that, and plug it into, put it right there. And we'll be done. So mu sub s times mg cos theta equals mg sine theta. Oh, look at that. Look at all the cancel-y things. I always love that. M's cancel, divide both sides by m. G's cancel, divide both sides by g. And we get the answer is that mu sub s is equal to sine theta divided by cos theta. And that, I think I taught you a little while ago that sine theta divided by cos theta turns into tan theta. So we can actually solve this on our calculator by saying theta max or something is equal to tan to the minus 1, which is a good button to know about on your calculator, of mu sub s. So luckily mu sub s is a dimensionless number that's between 0 and 1. So you can press tan minus 1 on your calculator and you get degrees out of it, some angle. And so the important thing here is that it doesn't depend on mass. So it's learning catalytics time. Hit deliver here. This is sort of related. And then we sort of have a demo, which I don't know if it's going to work very well, but are you guys ready to see the question? Again, I'll post these, but Idea. An empty box is on an incline, and it doesn't slip. So what I'm wondering is if you slowly add rocks to the box, thereby increasing its mass, will eventually you be able to get up to enough mass that it starts slipping or not? What do you think? Or does that sort of depend on the angle? Some angles, let you do a minute, and then share with your neighbor, chat with your neighbor if you have a neighbor. You guys in the balcony have neighbors? Find a buddy. Then we'll discuss it here. Okay. Adding pressure to our tennis ball launcher there, but yeah, so let me see what survey says. Maybe if you can click in 5 seconds, just a guess of this one. Going once, going twice. Let's do stop. It's good to remember 80% of this mark, 0.8 points, are just from your participation. But 52% of you are just voting for it doesn't slip. And I think what I'm trying to relate back to here is simply the fact that it doesn't depend on mass. If theta is less than theta max, that's it. And all it depends on is mu sub s, okay? That critical angle. So it's sort of weird. Oftentimes when you're thinking about things conceptually, or when you're thinking about things mathematically, it's almost two different sides of your brain or something like that. So you've just solved, it doesn't depend on mass. And yet, when your gut feeling is that you add more rocks, it should start slipping, but it doesn't. Do you want to try it with the aux plate? I don't know if this is going to work or not. There's both of these demonstrations I'm a little iffy about, but let's see what happens if I just slowly raise up the angle. There's going to be some critical angle where it'll start to slip. So let's go below that so it doesn't slip. And let's add more mass. It still doesn't want to slip. I would say no matter how much mass you add there, it's going to increase the normal force and it'll increase the gravity force. But remember those mg's kind of canceled, right? So it still doesn't want to slip. The only way to make it slip is to increase that angle. And then down she goes. And now it's kinetic friction, so it should just keep on sliding until it hits the bottom. So that pretty much worked. Yep. Question? Exactly. This means that you can measure the coefficient of static friction with just a protractor. Get to that angle where it slips, and then tan to the -1. Or tan. Right? You'll find tan of that angle equals mu sub s, and it's a good way of measuring mu sub s when you're making those tables. Okay, are we still here? So this next one, what time is it here? I think we do have time. I think it's important to do some of these problems that might be a little tricky. I have some steps to them. Question here is, what is the acceleration of a cart when there's a pulley and a hanging mass? It's the kind of thing that, you can sort of expect to see on a test. This one is just symbolic, though. But what we have here is two connected systems. Okay, we can either have this, think about the cart of mass m, uppercase M, or the hanging mass. So I can just quickly draw them. There's the cart. It's getting pulled upwards with some tension. And there's the hanging mass that's getting pulled upward, like really upward. This one just gets pulled up the incline with a diagonal force T, cart mass, capital M, and this is the hanging mass, lowercase m. Hanging mass. Okay. So the acceleration magnitude is the same. The tension is the same, and the acceleration is the same for both systems. So we're going to work out equations for both systems, and then we're going to remember the reason the acceleration is the same is because they're connected by a string that doesn't stretch. They are connected by a non-stretchy string. So if one moves up 1 meter, then the other one will move down by 1 meter, and sort of vice versa. So whatever their velocity or acceleration or position, or I guess is, it's going to be the same. So now in this stage, I'm going to draw a force diagram of, let's do the cart. So the cart is going to have its normal force of the surface on the cart. It's going to have the tension up the hill, and it's going to have this capital M G acting down. And I'm going to here define in this part just y up and x there, so that, and the other thing I'm going to do is assume that there's no friction on the cart. So I could have added friction there, but I'm not going to. So these are it. So the only diagonal force is gravity. The way I've tilted my axes is F sub g. So I'm going to say this Fg equals that. So if this is Fg, gravity acting downwards, then with my axes, I've only tilted them a little bit. Here's your angle theta. It kind of looks like this, I think. Mostly down and a little bit that way. So there's your right angle. This is your theta up here. This is negative F sub g in the y direction. And this is, now it's negative, the way I've defined it, F sub g in the x direction. So what I get here is that sine of theta is negative F sub g in the x direction divided by F sub g. And, sorry, I'm the margin here. Cos theta is negative F sub y, FGY over FG. So that's the force diagram for the cart. I want to draw a force diagram for the hanging mass. Let's do hanging mass. We will say that, well, this is how I found that, by the way, the theta. Did this a little earlier. If this is theta, this is 90 minus theta. So I think this is theta. 90 minus theta. So if you're wondering about how some of my reasoning there, I've tried to add that there. But anyway, hanging mass looks like this. Tension is going up. And the different force of gravity of Earth on little mass is acting down. And what I'm going to do here is define plus x is down. So that if this goes in the x direction, then the cart will also go in its own x direction. So the acceleration is in the plus x direction if it accelerates down. And so what I'm going to say here is that this way, the reason I did this, A is the same magnitude and same sign for the mass on the cart. Again, nice little tricks here. So cart. Now we're going to represent mathematically. The sum of forces in the y direction, I'm just going to take it from that force diagram. It's normal, minus FGY. So that's normal minus capital MG times cosine theta. And the sum of forces in the x direction is going to be tension minus FGX. So it's equal to T minus mg sine theta. So there's no y acceleration of the cart. No acceleration of the cart. So that means that the sum of forces in the y direction is equal to 0. And that's n minus mg cos theta. So we can already solve out for a normal force, mg cos theta. And the acceleration, x, is the sum of the forces in the x direction divided by capital M, the mass of the cart. We're still in the cart here. So it's t minus mg sine theta divided by capital M. I'm going to call that equation 1. And then for the hanging mass, which luckily its force diagram is still sitting there on the left, we've got just a sub x is equal to the sum of the forces in the x direction divided by lowercase m. So I'm using Newton's second law, both of these. And I get, it's just mg, little mg, minus the tension, which is up, because I defined x to be down. It's a bit confusing, divided by m. I'll call that equation 2. So I've got two equations, two unknowns. The unknowns here are a and t. We need the acceleration, that's what we're asked for, and we don't care about t, so we're going to solve for t and plug it in. About t, no one asked me for the tension, so solve for t in equation 1. So I'm going to use 1 to solve for t. A is equal to t minus mg sine theta over m. Sort of gathering like terms, I've got m times a equals t minus mg sine theta. Being very careful to distinguish between my uppercase m and my lowercase. So I got t is equal to capital M times a plus g sine theta. I'm going to plug this into 2. Thank you. I got a is equal to m, lowercase m times g minus capital M times a plus g sine theta. And I think all divided by lowercase m. And so you just solve it out. A is equal to g minus m over m, a minus m over m, g sine theta. Collect like terms of a times a equals g. You can pull out the factor of g in all these. 1 minus capital M over m times sine theta. So, and you can pull out the factor of m. A here, 1 plus capital M over m equals all this stuff. So I get a is equal to g times lowercase m minus capital M sine theta divided by little m plus big M. Not at all obvious, but we can check kind of limits if we want. That's what I like to do. If the cart is much, much more massive than the hanging mass, then you just get a equals negative g sine theta, like if little m was 0. And that kind of makes sense. If there's no hanging mass, things accelerate down the hill with g sine theta. Also, I would say if theta equals 0, then a is equal to g times lowercase m over the sum of the masses. We did that before when there was no slope. And also, I guess another one, if the hanging mass was much, much greater than the cart mass, then you get A is equal to G. That's if there's no cart, then the hanging mass just falls with 9.8. So that kind of makes sense too. Okay. That's it for 4.4. The next thing is to move on to projectile motion. So we've got a little bit of time, 20 minutes or so, to go over projectile motion. And I'll continue this on Wednesday. You can see some of you still copying this down. Yep. Oh, I assumed no friction force. I just made an assumption. But yeah, this would be the frictionless case. If there's friction, then that adds an extra complication, right? You'd have to put in F sub k or something. Good question. Okay. So this is this idea that if something's in free fall and it doesn't have any x component to its velocity, then it accelerates in the y direction downwards at 9.8 meters per second squared. Free fall, meaning that there's only one force on the object, and that is gravity. And all the other forces are negligible. But if something's moving, has a horizontal component to its velocity, then it goes in this sort of weird parabolic trajectory. Boing, boing, boing. So there goes that. So, and they're kind of separate. So I'm going to do second learning catalytics question. At time 0, ball 1 is just dropped. At the exact same moment, ball 2 is shot horizontally when a compressed spring is released. They're both steel balls, and the velocities here are pretty low, meaning that air resistance is negligible in both cases. So neglect air resistance. Which will hit the surface first? Some time to give you a minute to think about that. Okay. You guys got a vote? It seems like maybe some of you have seen this one before. Going once, going twice. And let's see what people said. Okay. You're saying both hit the surface at the same time, so that's exactly what I was looking for. The idea being that in both cases, a sub y equals negative g and a sub x equals 0 for both balls. Oh my God. This is so stupid. This is you, Morgan. I have to be real here. It's like, I was fixing a toilet the other day, and it's like, I'm real. Or, yeah. So you guys are now on Be Real. Okay. I'm really teaching physics in Con Hall. How about really get away from your phone sometimes, like leave it. Just walk in the park. No, I shouldn't give you a hard time. It is a nice little way to connect. Okay. Where was I? And so that's true for both balls. And also, this is really the key here, that V0 in the y direction equals 0 for both balls. And the reason that is the case here is that the ball 2 is fired in an exactly horizontal direction. So there's no y component to its initial velocity. So if you just kind of separate out the y and the x, and you just think about the y, they're both going to essentially be dropped from rest because there's zero y component. Okay? Because delta y, that's the other thing, is the Earth doesn't curve. Delta y is the same for both. Same for both. Okay? So let's see. So that's good. So then, yeah, going on, projectile motion, the idea here is that you have two independent motions, and that's the point of this monkey here, is that there's uniform motion, a constant velocity in the x component, and there's free fall in the y component. And the time is the same for both. And that's what leads you to the parabola. And there's all kinds of equations and stuff. But in other words, the x motion does not affect the y motion or vice versa. And of course, I'll just add the little thing. Neglecting air resistance. Neglecting. If there is air resistance, then the whole thing gets a little more complicated because the air resistance will depend on the speed, which has two components to it. But anyway, if there's no air resistance, you get this beautiful thing. And it really helps, too, because if you are standing still and you throw the ball up and you catch it again, where my tennis ball went, here it is. There's this idea that if we were driving along in a truck, okay, on the highway at 100 kilometers per hour and there are no windows, we would not be able to tell the difference between going at a constant velocity in a straight line and staying perfectly still. So I would throw that ball. It would actually go in this big parabolic arc, but I would only sort of see the y motion because that's the only accelerated motion. So you can, on your roller skates, you can still catch the ball. Okay. So, and another way of looking at it, if you have a diagonal speed where the y component begins at 19.6 meters per second, and the x component begins at 9.8 meters per second, again without the squareds, and I just plot its position, well, for every second of time in the motion diagram, the y component will change by subtracting off 9.8 meters per second, like per second, and so to go 9.8, 9.8, and then the x component just never changes. It's just 9.8, 9.8, 9.8, 9.8, whereas the y component goes to from 19.6 to 9.8 to 0 to negative 9.8 to negative 19.6. Okay. So we're going to do two learning catalytics. Where are we here? Let's do this one, and then we'll really shoot the monkey here. Okay, question. A tennis ball is launched at an angle, some angle, and flies through an air in a parabolic path as shown, A, B, and C. So you can imagine going A, B, C. All right. At point B, its highest point is A, the velocity is horizontal and the speed is maximum. B, the velocity is horizontal and the speed is minimum. C, the velocity is horizontal but the speed is neither a maximum or minimum. D, the velocity is not horizontal but the speed is minimum. Or E, the velocity is not horizontal and the speed is neither maximum or minimum. One of those I like a lot. Give you a minute to think, pair, share. Okay. Give me 10 seconds to click in. And going once, going twice. You stop you. Stop delivery. Up top 2, send all. Okay, the velocity is horizontal and the speed is minimum. So remember, the speed, I guess, velocity is a vector. So I think what's going on here is that the speed, v, is equal to the square root of vx squared plus vy squared. Does that make sense? So as you're going on a diagonal, what will happen is that at the top, Vy is 0, and Vx is constant. Never changes. Vx is just whatever V0 initially was times, this is theta, cos theta. If theta is a launch angle, then Vx never changes. It's always V0 cos theta through the whole path. But Vy starts off positive, goes to a minimum, 0, and then starts being negative. I guess it's negative, but the speed increases as it's coming down, decreases as it's going up, okay? And there's some equations that kind of look like this. You know, they're the equations of constant acceleration, but now she's just put them in terms of x and y. Okay, let's predict this one, and I'll be done. Gotta shoot the monkey. Idea here is that, I don't know if anyone here was a Bio 120 and was wondering what the heck is going on with this tennis ball launcher in front of Professor Cutter, but he agreed that I could set this up and leave it here, so thanks to him for playing nicely, and thanks to Pius for setting this up, and I wish you luck. Let me just describe it. The basic idea is that there's a monkey hanging way up in the air there from that balcony. Oop. Yeah, sorry, I pressed the wrong button. You see him? That's my daughter's monkey. And he is hanging from an electromagnet. So he's got it hanging onto a piece of metal. It's a very brave little monkey. And he's wearing, you know, some body armor in case he gets hit with a tennis ball, and he's going to be just fine. He's actually done this in the physics department. I don't know if he's done it in Con Hall before, but we're going to give it a try, okay? The electromagnet is connected to a wire which goes down here behind the curtain, over here, no trip hazard for your bio professor, so nicely, to a beam, an infrared beam, which crosses in front of the tennis ball launcher. So if a tennis ball breaks the beam, he's going to fall. So this is the whole idea, is that Pius has aimed, I don't know if you have a laser there, he's aimed this initial velocity to be directly at the monkey's heart. Can you kind of see it there? The little red dot? That's not mine. That's Pius's laser pointer, which is aligned with V0, the initial velocity of the ball. So if there was no gravity, the ball would just go up and hit him. So what's going to happen is that the instant the ball is fired, the monkey will be released and start falling. And then the question is, I guess maybe in real life, the monkey is hoping that the ball will go over his head or something like that. But we'll see what actually happens. Do you want to do a prediction? You guys do the prediction, and maybe let's just see what happens. I'm going to leave it to you, Pius. Do you want to try it? Do you want to do a 1, 2, 3? Or 3, 2, 1. Oh! Let's just make sure monkey's okay. Yeah, let's do it again. Okay, he's happy. He's fine. So we'll just put him right here. So it hit the monkey. So very good. I think a lot of you predicted that. Basic idea here is that the trajectory without gravity would have been right along the laser pointer and hit the monkey if he hadn't dropped. But what happens is that had the monkey stayed in the tree, the ball would have curved under its target as gravity causes it to fall a distance 1/2 gt squared below the straight line. So as time goes along, the y component of the ball's velocity decreases by 9.8 meters per second, or it goes in the negative direction, 9.8 meters per second for every second. And that is going to cause it to fall 1/2 gt squared below its zero gravity path every second. You can imagine that. So that's that distance right there. At any point, it's going to be 1/2 gt squared. Okay? At any point. So no matter where it is, as long as it doesn't hit the ground, no matter how far the ball goes, the monkey did the exact wrong thing, which is that he let himself fall a distance 1/2 gt squared while the ball is in flight. So when t gets to the proper x, like enough time so that the x distance equals where the monkey is, that's exactly where the ball is going to be to hit the monkey. So yes, the bullet hits the monkey, and we've just proved it that it actually kind of works. Okay. All right. So let's do a quick question from the back of your book, and then I'll dismiss. But this is problem 4.60. Good one, again, for studying for the term test. But basic idea is that an airplane is delivering food to a small island. It flies 100 meters altitude, 100 meters, and at a speed, a constant speed of 160 meters per second. Where should the parcel be released so it lands on the island? So what we're trying to do is imagine it's going to be dropped kind of from rest from the airplane, and it's going to fall on some little island here. We'll draw a palm tree. We need to find this distance x. Find x. And we're going to assume that v0 y equals 0 when released. So you can do this in a number of ways, but I'm going to define plus x to be that way and plus y to be down, I guess. So that a sub y is equal to plus g, which is 9.8 meters per second squared. And I say that vx is equal to x over t. That's the equation of zero acceleration, ax equals 0. There's only one equation for zero acceleration. And then what am I going to do? I have time as what I care about, and I think I don't care about v final in the y direction. I don't care how fast it's going in the y direction when it hits the island. I just care about the time. So I'm going to use that y is equal to v0 yt plus 1/2 a sub yt squared. And this is the same t for both. So that's the idea. I'm going to solve for x. I get here that x is equal to vxt. I need t. So I get 2 becomes, there's no y component, so it's 1/2 gt squared. So 2y over g is equal to t squared. So t is equal to square root of 2y divided by g. Take this and plug it into here. So I get x is equal to v sub x times square root of 2y over g. So it's equal to 160 times the square root of 2 times 100 meters is how far it falls, divided by 9.8. So I just get that x is equal to 722.8 meters. If it's one significant digit or something like that, we might round it and say x is equal to 700 meters. So you drop that parcel when the plane is 700 meters in front of the island. So on Wednesday, I'm going to finish up chapter 4, and then Friday we'll talk a little bit about the test and starting on chapter 5, even though chapter 5 won't be on the test. Something to think about. I'll say that no matter how fast your car is going, there's 4 points on the car that are at rest. So which are those 4 points? I'll tell you on Wednesday. Okay. Cheers.